Okay, we are moving right along with multidimensional calculus. Before we get into the actual calculus, I'm going to do a couple videos about n-dimensional Euclidean space. So this video is about space generally and specifically vectors and matrices. And then the next video will be about paths and curves, and then we'll get into differentiation. So this stuff, it's basically going to be me just presenting a bunch of definitions and things. All of vector calculus is based on matrices and vectors, so we need this stuff, and it's just good to have it down there so it'll put us all on the same page. So I've already done several videos on the dot product and the determinant and the cross product. So if you have not watched those yet, you should. I'll link to them right here. Okay, so first, vectors. So we're talking about points in Euclidean space, and Euclidean space is just space of some dimension. R1 is a line, R2 is Cartesian coordinates, and then R3 is space that we live in. And then it goes up from there, and then it's harder to picture because we live in three-dimensional space. But in three-dimensional space, we think of vectors in three ways. It's like a triple, like XYZ, with X, Y, Z, and R, a point in space, or a directed line segment. So we can't really think about vectors in higher dimensions as a point in space, because again, we can't really picture what a five-dimensional space looks like, or same for a directed line segment, but we can certainly represent them like this. So we define Rn, where n is a positive integer, as the set of all ordered n tuples, x1, x2, to xn, where these are all real numbers. So Rn is called Euclidean n space, and if we can think of x as an element in Rn, and we can think of them as vectors, or sometimes they're called n vectors. So addition and scalar multiplication are defined as, you can guess because they're parallel to 3D. If we have a1, a2, an plus b2, bn, it equals a1 plus b1, a2 plus b2, an plus bn. Okay, so you just add them one by one. And for scalar multiplication, alpha times a1, a2 is alpha a1, alpha a2, and so on. Okay, that's easy. Now there are particular vectors in Rn. E1 equals 1, E2, and En. These are called the standard basis vectors, and they basically are the generalized notion of I, J, and K, which we talked about a lot in the cross product videos and the dot product video. So using these, you can write one of these vectors as AE1 plus AE2 plus AEN. Okay, so all that's straightforward. The dot product, or inner product, is defined the same as in R2 and R3. A dot B equals A1 B1 plus A2 B2 plus up through AN BN. And then the length of a vector, or the norm of a vector A, is defined as, you write it like that, and it's defined as the square root of A dot A, which if you expand that, it's the square root of A1 squared plus A2 squared, the square root of the whole thing. And this is just the extended Pythagorean theorem, right? Which we also talked about before. If you have A and B, then A squared plus B squared is C squared, so the square root of A squared plus B squared is this length here, right? That's all this is in multiple dimensions. Note that since the norm of A is the square root of A dot A, you'll frequently see basically the length of A squared, which is the same as A dot A. So when we're talking about length, we might talk about the norm squared or A dot A, which remember is the length squared. Now, algebraic properties. 1, A dot A is always bigger than or equal to 0, and it equals 0 if and only if A equals 0. Scalar multiplication is basically associative. If we have alpha times of A dot B, that equals alpha A dot B, and alpha of beta dot b equals beta alpha dot a dot b. And it's distributive. So if we have a dot b plus c, that equals a dot b plus a dot c. And it's distributive in both ways. So we can also have that a plus b dot c equals a dot c plus b dot c. Finally, it's commutative. So these are all algebraic properties of the dot product, basically, and the scalar multiplication and addition. They're all easy to prove, so I'm not going to bother here. If you want, ask me. We can go over it in another video at some point. Okay, next up, the Cauchy-Schwarz inequality. So using all of our algebraic properties, we're going to prove the Cauchy-Schwarz inequality algebraically. And so one thing that I want to say here, because I'm going to say this again, because we're in higher dimensions, it's not really possible to represent these things geometrically. You can sort of try to stretch your brain, but it doesn't really work very well. And it's better to get used to thinking of this stuff purely algebraically. So that's what we're going to do here. And then we're going to define some geometric concepts in terms of the algebra, rather than looking at pictures and then describing those pictures algebraically. And this is also the way that Alfors in the complex analysis book, it's how he approaches complex analysis as well. In some descriptions of complex numbers, there's a heavy emphasis on the geometry of it in order to sort of justify the different operations. But Alfors, well, I'll show you this more when we get to complex analysis, but he starts with the algebra, and then he uses geometry to sort of illustrate the different operations, but he emphasizes that what we're constructing is an algebra here in a mathematics, and then the geometry will help us to understand it, but not to justify it. So we're sort of doing the same thing here. So, okay, the Cauchy-Schwarz inequality, it says that for vectors A and B in Rn, we have that the absolute value of a dot b is less than or equal to the norm of a times the norm of b. Okay, proof. If either a or b is 0, then the whole thing just becomes 0 is less than or equal to 0, right? Because 0 dot a is 0 and b, and if either one of these is 0, this whole thing's 0, so it's just 0 dot 0. So we can assume that both of them are bigger than 0. If that's true, we have the following inequality, that 0 is less than or equal to. So this is a normalized vector, which means that the vector might have any length. It could be very short or it could be very long, but we divide it by its length, and then we end up with a vector in the same direction that is 1 unit long. So both of these are 1 unit in length. And then here again, as I just said, this is the norm squared. So this is the vector from B to A. So this is the length of the vector from B to A squared. And this equals, I'll just write it down and then we'll look at how we got there. So where we get this is, if we just write this out using distributivity, we have this is the same as A over A minus B over B dot A over A minus B over B. And again, so this is one vector that goes from B to A. And so we're dotting that together. Okay, so if we just distribute this, we'll use this one and distribute it. No, we'll distribute this to this and this. So that equals A over A minus B over B. Right, so we just distributed this between these two. Then we do the same thing again, distributing this over those two. Okay, so the length of this is 1, the length of this is 1. So if you dot them together, it's going to be 1 squared, which is 1. Same here, that's 1. Now this, if you dot these together, we can take out the fraction and dot these, right? So it's just, this is A dot B over, right? Because these are just scalars, so they multiply. So we're dotting these and then multiplying by 1 over AB. There's 2 of them, and it's minus. Okay, that's where we got this. So if we take this now and just simplify it, we have that 0 is less than or equal to this thing. So this is just 2 minus 2AB over AB. Let's move this to the other side, and we have that 2A dot B is less than or equal to 2. Cancel those. make that 1. And we have that a dot b over ab is less than or equal to 1. If we multiply both sides by ab, we have that a dot b is less than or equal to a b. So now, if we did this exact same proof, but we used a plus sign here instead of the minus sign, then we would get exactly the same proof, except that there would be a plus sign throughout here, and we would end up with a plus sign here, which would mean that this would go over as minus, and what we would end up with is a minus here. We would end up with minus a dot b is less than or equal to the length of a times the length of b. So both a dot b and minus a dot b are less than or equal to the length of a times the length of b. That means that the absolute value, it doesn't matter, the sign doesn't matter, is less than or equal to, which is what we wanted to prove, right? That's the Cauchy-Schwarz. Okay, good. Now, if a and b are both non-zero, then a dot b divided by both their lengths is a number between. And remember, the dot product always gives you a number, not a vector, right? So this is a number and this is a number. So this number always lies between -1 and 1. Any number that lies on the interval -1 to 1 is the cosine of some unique angle theta between 0 and pi. So using this information, we can define what an angle is in higher dimensions. The angle is the inverse cosine of, and if you think about it, this is just the other definition of the dot product, because if we took the cosine of both sides, then we'd have cosine theta equals a dot b over ab, and then we multiplied ab by the other side, and we would end up with ab cosine theta equals a dot b. Right? So this is a familiar formulation of the dot product, and if we just rearrange things, then we can end up with theta, and this is our definition of an angle in higher dimensions. So again, we can't really talk about what an angle in R5 actually is. We can't really picture that, but we're just defining it algebraically. So this is what we mean when we talk about an angle between two vectors in higher dimensions. Okay, next, the triangle inequality, which we can derive from Cauchy-Schwarz. The triangle inequality says that if we have a and b are elements of Rn, then the length of a plus b is less than or equal to a plus b. This is just a fact about geometry that we've known forever, right? That if we have a here and b here, the length of one plus the other is always going to be longer than the hypotenuse. Okay, but to prove it, start with another equality. The length of a plus b squared equals the length of a squared plus 2a dot b plus the length of b squared, and that is less than or equal to the length of a squared plus 2 times the length of a times the length of b plus the length of b squared. And the reason this inequality is true is that the a's are the same, the b's are the same, but this is less than this. This is Cauchy-Schwarz, that the a dot b is less than the lengths multiplied. That's Cauchy-Schwarz. So this is true. Now on the right-hand side, a squared plus 2ab plus b squared, we can rewrite that as, right? A squared plus 2ab plus b squared. So the length of a plus b squared is less than the length of a plus the length of b squared. Take the square root of both sides, and you have less than or equal to. There you go. Next page. If we want to, we can also write Cauchy-Schwarz and the triangle inequality in terms of their components. So Cauchy-Schwarz, let's see if we can do this. So this would be the sum of the components, right? The absolute value of that is less than or equal to, and then this is the sum from I equals 1 to n of ai squared, the square root of that, and then the square root of bi squared, right? Then the Schwarz, or the triangle inequality, this is the square root of the sum of a plus b squared. Square root of that is less than or equal to I equals 1 to n of ai squared, square root of that. Okay, so we can also analogize the notion of distance in higher dimensions. The distance between two vectors in Rn, if a and b are elements of Rn, is just the distance between the two. It's A minus B, and remember, if you have A and B, then A minus B is from the second one to the first one. So this is A minus B. The length of this is the distance from the end point of one to the end point of the other. So this is our definition of distance in Rn. Okay, the determinant. Now first, remember, there is no cross product in higher dimensions. There's only a cross product in R3 because when you have a parallelogram, it's only in R3 that there's a unique vector that's perpendicular to this plane. In higher dimensions, that's not true. So the cross product doesn't really work. But the determinant can be generalized. And remember, in the previous videos, the way that I want to think about the dot product is that the dot product is kind of adding like components. So you multiply the components going one direction and then the components going the other direction. So the dot product is kind of a measure of how much the two vectors are going in the same direction. And so if they're parallel, then it's going to be the same as if you're just multiplying the scalars. If they're perpendicular, they're not going in the same direction at all, and the dot product is 0. The determinant, in some sense, is the opposite of that. It's taking each component and multiplying it by all the other components across the board. So in 2 dimensions, you end up with the area of sort of the sweep between them. So A is going this way and B is going this way, and the determinant is the area here. So the determinant is the opposite of the dot product. If they're perpendicular, then it's going to be A times B. But if they're parallel, then they would collapse on each other, and the determinant would be 0 because there's no area between them. And then anything less than perpendicular is something less than the area of the rectangle. That's the determinant. So remember that when one is at its maximum, the other is 0. When the determinant is at its maximum, the dot product is 0 because these are perpendicular. When the dot product is at its maximum, the determinant is 0. Okay. Moving on, matrices. The thing to remember about a matrices is that they're very simple. It's just an array of numbers, and yet it can be used to describe surfaces or lines and derivatives in multidimensional space and everything else just by having an array of numbers. So it boils down what is too difficult to picture into a very simple, m by n matrix. When we get to the actual calculus, the matrices are a big part of how we do multidimensional derivatives. So an m by n matrix has m rows and n columns. So it's always hard to remember which comes first, the row or the column. In Excel, it's column row, right? If you have a cell C3, it's column and then row. But you can also refer in Excel to row column form. And the way to remember it is that we're using row column, and also you never hear the phrase column row. It's always row column. That's how matrices are. It's row, then column. But then, of course, it's all completely arbitrary because then when we're looking at coordinates, it's column and then row, right? So you never know, but matrices are row column. So an entry in this matrix, Aij, is the ith row and the jth column. And sometimes we'll write the whole matrix as Aij. So a square matrix is, of course, one where m equals n. So addition and scalar multiplication are the same as for vectors. So addition, if you have two m by n matrices, A and B, then we can define C equals A plus B by component-wise addition, same as we do with a vector. So for example, if we had, all you do is you add them one by one. So that's 1, 2, 3, and then 3, 4, 8. Okay, easy. Scalar multiplication is also the same as with vectors. Very simple. You just take the scalar, if you have a scalar lambda, and you multiply it by each element in the array. So for example, if we have 3 times, that's going to equal, just multiply 3 by each one. We have 3 minus 3, 6, 0, 3, 15. Okay, good. So now the most important operation on matrices is matrix multiplication. So if A is an m by n matrix and B is an n by p matrix, then AB is an m by p matrix whose ij entry is Cij, k equals 1 to n of a, I, k, b, k, j. This is one of those things that it looks so ugly, it's easy to just kind of shut down to and just say, okay, I don't know what you're saying, whatever, okay. What this is the dot product of the rows of A and the columns of B, okay? That's the way to remember this. So if we have, let's make an array here. So if we're going to multiply these two, AB equals, so we're taking the dot product of each row in A times the column in B. And that's how we end up with our element. So this is an M by N, and this is N by P. So in order for multiplication to work, it's M by N, and this is N by P. The columns in A have to be the same as the rows in B. So, and the reason is because we're taking the dot product of basically this vector and this vector. We're taking the dot product of them to come up with the entries for the new matrix, and the new matrix has size M by P because we're doing it 3 times here and 3 times across. So there's 3 and 3, okay? So each entry, so we have to take the dot product of each one of these. So it's 0, 0, 0, and then the next one over, 1, 0, 3, so add that's 4, and then 0, 0, 3. Now second one down, 0, 1, 0 is 1, 2, 0, 0, 2, 0, 0, 0, and then 0, 0, 0, 1, 0, 0, and 0, 0, 0. Right? Okay, now, what's really bizarre about matrix multiplication is it's not remotely commutative normally. So BA is not going to be the same. So if we do B times A, now we're going across and down, right? So we have 0, 2, 0, 0, 1, 0, and 0, 0, 0, and so on. These are not the same at all. So generally, matrix multiplication is not multiplicative, or it's not commutative. So for AB to be defined, the number of columns in A has to equal the number of rows in B, because these are the two that we're taking the dot product of, right? But the number of rows in A does not have to match the number of columns in B. So for instance, we could have that A is and B. Now, will this work? We're taking a vector, the row here and the column here. We're dot producting these two. 3 here and 3 here, so you can definitely take this. When we multiply them, we have a 2, 0, 1, that's 3, 0, 0, 1. The columns in A have to be the same size as the rows of B, but the rows in A do not have to be the same as the columns in B. So one thing to notice here is that we actually cannot multiply BA here because the number of columns here does not equal the number of rows. So B times A is simply not defined. But then look at what that means. It gets really weird. So A equals 1, 2, 1, 3. B equals 2, 2, 1, 2. Now if we want A, B, columns here is 1. The rows here is 1. So this is defined. So what do we have? This, if you dot 1 and 2, you just get 2. If you dot 1 and 2, you just get 2. So all we're doing here is just multiplying 1 by each one of these. Then we do the same thing for the next row. 2 times 2 is 4. And then you just go across. But what if we do BA? Is that defined? Well, for BA to be defined, we have to have the same number of columns in B as rows in A. We do, so we can dot product, we can take the dot product of this row and this column. So we have 2, 4 is 6, 7, and 6 is 13, and that's the whole matrix. So it's totally bizarre that if we multiply them one direction, we get a giant square matrix that's 4 by 4. If we multiply them the other direction, we just get a matrix with a single element in it. Okay, matrix multiplication is associative. So AB times C equals A times BC. which means that we can also just write A, B, C, and that's perfectly fine. That's also easy to prove. We're not going to bother proving it. If you want me to, I can, let me know. Okay, so vectors and matrices. Vectors are usually written like this, but we want to be able to use them with matrices. And the way to do that, a good way to do that is like this. You can write it like this instead. So this is called an n by 1 column matrix. You would also call that A. And it's also possible to do this as a row matrix, which is a 1 by n row matrix. And the row matrix, the 1 by n, would be the transpose of the column matrix. Transpose is when you flip something along the diagonal. So if A is an m by n matrix, and x is a vector in Rn, then we can write the matrix product of A times x and then if we did this multiplication, we dot each row with each column, right? So the result will be this row and this column dotted down through this row and this row column and this column. So it would be y1 to yn. Oh, actually to ym. So this would actually have the number of rows in the matrix instead of the number of rows in the vector. So in that way, then A defines a function from Rn to Rm, defined by y equals ax. Sometimes we write this, which is called a linear transformation, because it has the linearity properties, which are a of x plus y equals ax plus ay, and a of alpha x equals alpha of ax. This is for all x and y in Rn, and this is for x in Rn and alpha in R. So let's go to the next page. And let's look at an example of this. If we have A equals this matrix, it's 4 by 3. So it's important to notice something here, which is that A is not an element of Rn or Rm. It's something different. A is a function. It's an operation or a transformation from Rn to Rm. So matrices are strange in that way because they represent both vectors. You can have x1. They do represent vectors, but then they also represent something else. They represent functions, such as this. So the important thing to see here is that the domain of A is the number of columns, and the codomain or the range of A is going to be in R4. So it takes elements from R3 and puts them into R4. So you can actually map vectors from one space into a different dimension in a different space. So okay, so let's look at A again and see what we have. So here we're changing something from three dimensions into 4 dimensions. So let's see how that would work. If we have x is, and we want to remember, so we're going from x to ax, right? So next is A, and then x. So how does this work? What do we end up with? We have x1, 0, and 3x3, minus x1, 0, and x3, so A translates a vector in R3 into a vector in R4 in this way. So this looks like a lot of information here, but the only information right here is the array, or is the matrix A. All the rest of this is just explaining what this matrix does. This is all just a representation of what A is telling us to do. Okay, so let's try it for real. What will A2 do to E2? Which is 0, 1, 0, right? So let's try applying A to E2 times 0, 1, 0. So we go 0, 0, 0, 0, 0, 0, 0, 1, 0, and 0, 2, 0. So what is this? It's just the second column of A. So we took E2, which is just a 1 in the second column of E2, and we translated that into the second column of A. Interesting. And then in addition, it took a 3-dimensional vector and translated it into a 4-dimensional vector. So let's change pages again. Now, an n by n vector matrix is invertible. Let's say, so an n by n matrix A is invertible if there exists an n by n matrix B such that AB equals BA equals I, where IN equals So this is the identity matrix, and the identity matrix, just like with real numbers, has the property that C times the identity times C equals C for any n by n matrix. So we call B is the inverse of A, and the inverse, when it exists, is unique. But remember, not every matrix is invertible. So it's important to understand that this is very different from fields of real numbers, because the matrices do not make a field. Even square matrices do not make a field, because not every matrix has an inverse, which is one of the requirements of a field. And we already said that matrix multiplication isn't commutative, so there's already problems, but here's another one. So matrices are not at all a field. Okay, so let's just try one. If A equals, then A inverse equals, then the inverse equals 1 over 20 times all that. Because in this case, A times the inverse of A equals I equals the inverse times the original. So let's just make sure that this is true. So in the first row in the first column, we have 8 and 12 and 0. So 8 plus 12 is 20. And then we have minus 16 plus 16 and 0 is 0. And 0 minus 4 and 4 is also 0. And 20 times 1/20th is going to be 1. For the second row, we have 0, 6, minus 6, that's 0, 0, 8, and 12 is 20. And then 0, minus 4, and positive 4 is again 0. Again, 20 times 1/20th is 0. Third one, 12, 0, and minus 12 is 0. Minus 24, 0, and 24 is 0. 12, 0, and 8 is 20. Times 120, so it's 1. Okay, so it worked. It's interesting because when we're doing real numbers, finding the inverse of the multiplicative inverse of a real number is really straightforward. Finding the multiplicative inverse of a matrix isn't straightforward at all. This is just ugly. You can't eyeball this and see why this would be the inverse of that, which of course is what solving systems of equations is all about. Okay, so one more thing here. If A is invertible and AX equals Y, then A is invertible. So if we multiply the inverse of both sides, and these cancel, and we have that X equals A to the 1 negative Y. So if A is invertible, then if AX equals Y, then X equals the inverse times Y. Okay. So determinants. Should say more on determinants. So 3 by 3 determinant can be generalized to n by n. I don't find it hard to understand where you get the determinant. If we have just a 4 by 4 matrix, to me finding the determinant is easy because you take one row or one column and you take that one times the what's called the minor, which is basically the determinant of what's left, and then you take this one times the determinant, which is this row and these two rows, and then this one times these two rows in this row, and this one times the determinant here. And then to find the determinant of a 3 by 3, you do the same thing again. The only difficulty is remembering that you have to alternate the sign. So the first one, this times this determinant is positive, the next one's minus, the next one's positive, the next one's minus. Except for that, to me, the determinant's easy to remember because in each case, you're multiplying each element by the other elements. So you're multiplying the first times the other 3, second times the other 3, and so on. So the properties of determinants hold for higher dimensions. I'm just going to list them. Rule 1, and I'm just numbering them because it's the order that I'm saying them to you. This isn't something that we're probably going to use. But the interchange of any two rows or any two columns changes the sign of the determinant. Rule 2, the determinant of a matrix with two identical rows is 0. Rule 3, we can factor scalars out of any row or column. So for example, for 2 by 2, what that means is here we can factor an alpha out of the first column, the second column, the first row or the second row, and in every case we can just factor out that alpha out of the determinant entirely. Or of course that means that we can move it from here to from one column to the other, from one row to the other. All of these are equal. Two more rules. Rule 4, if any row or column consists of zeros, then the value of the determinant is 0. Rule 5, if we change a row or column by adding any multiple of another row or column to it, the value of the determinant stays the same. So for Rule 5, let's look at what Rule 5 means. Okay, so this looks like a mess, but it's not that hard. So what we're doing here is we're, in each one of these, adding one row to the other, to a multiple of the other row. So here, the first matrix is A1, A2, B1, and B2. So here we take B1, B2 and add a k multiple of it to A1. So the first row becomes A1 plus KB1, and then A2 plus KB2, right? So same thing here, this time we're going down. So we're adding a k multiple of A1, A2 to B1, B2. So it's B1 plus KA1, B2 plus KA2. And then we can add columns the same way. So here we add a multiple of A2, B2 to A1, B1. Here we add a multiple of A1, B1 to A2, B2. Okay, so this is just the generic way of saying what we learned in high school about solving systems of linear equations. So a basic theorem of linear algebra states that an n by n matrix is invertible if and only if the determinant is not 0. Then another basic property is that the determinant of A times B equals the determinant of A times the determinant of B. Okay, let's do one example to bring all this together. So let A equal this. So let's find out, does A have an inverse? So if we can get rid of this 1, we'll have 1, 0, 0, 0. That would be good. So let's just subtract row 1 from row 3. In other words, multiply this by -1 and add it to row 3, and that will make this a 0. So we'll end up with, right, we subtracted this one from this one. So it was 1 minus 1 is 0, or I'm sorry, 1 minus 1 is 0, 1 minus 1, and then 0 minus 2, and 0 minus 1. Okay, now we can take the determinant here. These are all 0, so it's just this times this, 1 times. Now, what can we do with this one? Well, we can subtract this one from this one again, and we'll clear that 0 once again. So again, we have zeros here, so we can take this determinant again, and we have, right, this is 1, and that's 1 times this, so it's just this equals minus 2 times 1 is minus 2, minus 0 is minus 2. Minus 2 is not 0, so A does have an inverse. Okay, that is everything we need to know about vectors and matrices in Rn. And with that, next up is curves in the plane and space. We're really getting toward multivariable calculus fast. We just have to get these foundational things down, and then we'll be ready to go. See you next week. Okay, here is the link to the first video in this chapter. Here is the link to the previous video. Here is the link to the next video. And click here to subscribe, and please join me on Patreon. The link to that is below in the description. Thank you.